Hello everyone. The title of this video is Verifying Solutions to Homogeneous Linear Systems or Homogeneous Linear Systems. So in this video, this might be a short one, I'm hoping. I'm just going to be looking at a linear system of equations that's homogeneous, first order as well. And I'll be given a solution to that system, and then I just have to verify if it really works. So this is just going to be a lot of substitution and checking that the system is indeed correct with this particular solution I'm given. Very simple stuff. All right, so I've only got a couple of these. All right. So I'm asked to verify that the vector x is a solution of the given homogeneous linear system. All right, so you might recall from a previous video, I'm going to write these systems in matrix form if they're not already. So this would be vector x prime equals, and then here we have a 2 by 2 matrix. First column has the coefficients of x, 3, 4. Second column has the coefficients of y, -4, -7. And then times, vector x, where vector x consists of some functions, say x of t and y of t, right? Vector x consists of the unknown functions x of t, y of t. Okay, so what I'm going to do is I'm just going to substitute this vector into this equation and see if we get a true statement. So we're trying to verify, is this a solution, this vector? Is this vector x a solution of this system? Now, this vector x here, if you want to write it more condensely, is e to the -5t for x of t and 2 e to the -5t for y of t. All right, and then if I want to substitute and check, I need x prime. Right? So x prime, vector x prime, is simply taking the derivative of each vector component from x with respect to t. So this would be -5 e to the -5t, and then -10 e to the -5t, and if you'd like you can pull the e to the -5t out and have vector -5, -10 times e to the -5t, same thing. Alright, so now I just substitute and check, is this equation going to be true with this particular vector? So x prime, that's this thing here, -5 e to the -5t, -10 e to the -10t. Is this equal to this 2 by 2 matrix, 3, -4, 4, -7, times the vector x, which what we're checking here is this e to the -5t, 2 e to the -5t. Okay, now I'm just going to multiply these two matrices. Now this is a 2 by 2 matrix multiplied by a 2 by 1 matrix, so this result will be a 2 by 1. In the first row, first column, I'd have the first row of the left dot product with the first column of the right matrix. So this is 3 e to the -5t minus 8 e to the -5t for the first row, first column of the product. Then for the second row, first column of the product, take the second row on the left, first column on the right, dot product, that'd be 4 e to the -5t minus 14, right, now 7 times 2, e to the -5t, and oh look, those are indeed the same. Because look, 3 minus 8, that'd be -5, e to the -5t, fantastic, same as the first row, first column on the left. And 4 minus 14 is -10, you'd have -10 e to the -10, why did I put -10t here? should be negative 5t. My apologies. But yeah, so that's negative 10 e to the negative 5t, and that's indeed the same exact as the second row, first column on the left side. So yes, this vector we were given is a solution. We have now verified it. Check. Right? It's as easy as that, right? Just like checking solutions to anything. Right? You just plug them in, see if they work. See if you get true statements. All right, so I've only got one more of these where it's already written in, the system is already written in matrix form. It's another homogeneous system because you got, some matrix times the vector x plus the 0 vector, right, which makes it homogeneous. All right, so vector x here, again, I personally like to put it in, make this is negative e to the negative 3 halves t, right, 3t over 2 or 3 halves t, and then positive 2 e to the negative 3 halves t. All right, then x prime would be, doing the derivatives of these, be a positive 3 halves e to the negative 3 halves t for the first component, first row, first column, and then negative 3 times e to the negative 3 halves t. Right, using the chain rule and all that. All right, so let's substitute these into my system here and see if we get a true statement. So x prime, we have, again, the 3 halves e to the negative 3 halves t, and then negative 3 e to the negative 3 halves t equals, and then the matrix, the 2 by 2 matrix here, negative 1, 1/4, 1, negative 1, times x, and again plugging this in, this x, negative e to the negative 3 halves t, 2 e to the 3 halves, negative 3 halves t, and then we multiply these two matrices here and see if the left side and right side are indeed equivalent. So again, a 2 by 2 times a 2 by 1 will be a 2 by 1. 2 by 1. First row, first column will be, positive e to the negative 3 halves t, and then plus a half. All right, 2 times a fourth plus a half e to the negative 3 halves t. And you see how that's actually equal to the first row, first column on the left, right? This is 1 plus a half e to the negative 3 halves t. 1 and a half is 3 halves. So the first row, first column entries are the same. And then second row, first column would be, negative e to the negative 3 halves t minus 2 times e to the negative 3 halves t. And combining the like terms here, combine the coefficients, you do indeed get the same as the second row, first column over here, negative 3 e to the negative 3 halves t. So these are indeed the same. And this vector we were given initially is a solution. So we have verified this. Check. Okay, pretty simple. All right, I'm hoping I don't need to have to do more than these couple examples to demonstrate how to check if something's a solution to a system. All right, and hopefully watching me go through these couple help you out when you're working on similar problems on your own. And thank you very much for watching.